All right, so my goal for today is to go through the notes, which aren't terribly long, I don't think. Do a little bit of a preview of the homework, especially the homework for Wednesday, because it's set up a little bit differently than some of the other homeworks that we've talked about so far. But we'll get to that when we reach kind of the end of class today. So let's see here. Do some screen sharing. That's the one we want. All right, nice. So we are in week, where are we at? There we go. Week 3 of this weird little short term 4. So as Gerson was talking about earlier today, we have this week, then we have next week, and that is it for term 4. So next Thursday, April 1st, will be the very last day of class for this term. And then the next week on Tuesday, we'll start back with the first day of term 5. So today we're going to be talking about electric charges. Again, how do things get charged? How do we move these electric charges around? Because remember, physics is all about motion and how things move. And so we're going to talk a little bit about how movement relates to electricity. Give it a second here to load up. There we go. Oh, this is different. All righty. So the first thing that we have to kind of understand if we want to start talking about electricity is, where does electricity and electric charge come from? So these charges that we're going to be talking about, there's positive and negative charges, and they come from tiny little particles called atoms. You've probably heard of atoms before. They're super duper microscopic. You could fit about 1 million of them across a single pencil dot, like a period at the end of a sentence. They make up all of the matter in the universe. So all of the stuff in the universe is made out of atoms. Everything on Earth, everything in the sun, everything on Mars, everything in outer space, it is all made of atoms. So if you took IPC with me here at the Excel Center, you've probably heard lots about atoms and the periodic table and protons and neutrons and electrons before. If you haven't, don't worry, we're just going to be talking about the very basic different parts of the atom today. So even though atoms are super duper tiny, itty bitty microscopic, even atoms are made up of 3 different types of particles. There are protons, which are the little green balls in this picture over here. Protons have a positive charge. So 1 proton is 1 positive charge. So they're a lot of times represented by this plus sign. There are neutrons, which on this picture are represented by the little purple balls. They hang out with the protons in kind of the center area of the atom. Neutrons do not have a charge. They have 0 charge. They're totally balanced. They're not positive. They're not negative. They're like a 0. So since the neutrons are neutral, they're sometimes represented by a 0 for not having any charge. Finally, our electrons are separate from the protons and neutrons. They're kind of whirling around the outside of the atom on these little rings right here. If you took IPC with me, you got to hear all about electron rings and shells and stuff like that. But today we're just going to focus on the electrons themselves. Electrons have a negative charge. So while protons are positive, electrons are negative. So electrons are sometimes represented by these little minus symbols. So we have our positive protons and our neutral, 0 neutrons hanging out in the middle of the atom right here. And then circling around them on the outside of the atom are our negative electrons. And these negative electrons are what we're really going to focus on today, because they are where electricity and electric charge comes from. It's all based on moving these electrons around. So protons and neutrons don't move. They're stuck together. They stay in the middle of the atom. Electrons, though, can sometimes move between atoms and between materials. And that's a lot of what we're going to talk about today, is how these electrons get moved around. So when we move electrons from one atom to another, or from one object to another, we can build up what's called an electrical charge. So if you have too many electrons, if you have lots of electrons on a material, that material becomes negatively charged. So the overall charge of the material is minus, negative. On the flip side, if your material has lost a lot of electrons, so it has too few electrons, it doesn't have very many on it, that causes it to become positively charged. So if we have lots of protons and very few electrons, we end up with a positive charge. And then finally, if our protons and electrons are balanced, if there's the same number of electrons and protons, then we call that a neutral atom, or the charge is neutral, meaning it doesn't have any excess negative or positive charge. So most atoms start off as being neutral atoms. They have balanced number of electrons and protons. If an atom gains a whole bunch of extra electrons, then we have a lot of minus charges and a few positive charges. So we end up with a negative charge on our atom. Or if that balanced neutral atom loses a lot of electrons, if it gives away a lot of its electrons, before it was balanced with the positives and the negatives. But if our positives stay the same and the negatives go way down, we end up with an overall positive charge. So that's what I mean when I talked about how electricity and electric charge is all about moving these electrons around. The protons and the neutrons stay still, but if we give a bunch of electrons to something, it becomes negative. And if something loses a bunch of electrons, if we take away a bunch of electrons from an object, it becomes positive. And that's how we build up electric charges, either negative charges or positive charges, is by overloading them with electrons or stripping a bunch of their electrons away. So one of the key ideas of electric charges, in fact, it's so important, they call it the electric charge law, or the law of electric charges, is that like charges or similar charges repel each other, and opposite charges attract. So if we have two materials that are positively charged, they have lots of protons and only a few electrons, then they are naturally going to push each other apart. Same thing with if you have two different objects that have a lot of extra electrons on them. If they're both negative, then they're also going to push each other apart. They're going to repel each other away. So this is like if you've ever played with magnets before, you know there's the two different sides to the magnet. And the one side, if you try to push the same side of the magnets together, then you get that kind of, it's hard to get them to push together, right? You feel a little bit of resistance when they get close. It's the same basic idea. Those are similar sides of the magnet, and so they naturally push each other away. Same thing with electric charges. Positive and positive, or negative and negative charges will repel each other, will push each other away. On the flip side, opposite charges attract each other. So positive and negative charges are naturally attracted to each other. It's like when you turn the magnet around and you bring them close and then the magnets slam together. That's because you have the opposite sides that are attracting each other. Same thing with electric charges. Opposite charges attract each other. They become attracted to the opposite charge. So since our protons are positive and our electrons are negative, they are naturally attracted to one another. That's what helps kind of keeps the electrons close in to the protons and neutrons, is because the negative and the positive are attractive. So like charges or similar charges repel each other, they push away. Opposite charges attract each other. Plus, positive and negative charges naturally want to come together. So if you have two like balls on a string or balloons on a string, if both of your balloons are positive, they're naturally gonna remain apart from each other and kind of be pushed away from each other. Same thing with both of your balloons are negative. On the flip side, if you have a positive balloon and a negative balloon and you hang them from strings, they're naturally gonna pull together and want to be close to each other. Opposite charges attract, like charges or same charges repel, push each other away. All right, so while we're still on the basics of electric charges, does anybody have any questions so far on parts of the atom, positive, negative charges, or how they interact with each other? All righty. Does not sound like it. So we've got our positives, we've got our negatives. If they're the same, they push away. If they're different, they attract. So how strongly that they push away or how strongly they attract to each other is something that we can calculate as physicists. It's something that we can measure and use a formula in order to figure out. So we call it the electric force, the force between two or more charged objects. So our positive, positive, or our negative, negative, or our positive, negative, when they get close to each other, there's an electric force between them, either a force that's pushing away or a force that's pulling together. So how strong this force is, the size of the electric force, depends on two different things. How many charges and how close are they? So the bigger the charge on your objects, like the more protons or more electrons that you have on your objects, that's going to create a bigger force between them. So two things that are really negative, that have a ton of electrons, are going to push each other away more strongly than two things that are just a little bit negative. And then also the distance between the charges. The further away that you get, the less force that there is between these charges. So in general, the charges have to be pretty close to each other in order to exert this force, right? If we talk about this attraction or repelling force, it's not going to happen if you're holding your objects really far apart from each other. They're going to just move around all on their own. It's only when you bring them close to each other that they start repelling or attracting. So how big is your force and how close are your objects will determine how strong of a push or a pull those objects, those electric charges, are going to exert on each other. So again, the strength of the electric force depends on the size. More charge means more force. And the distance. More distance means less force. So the further away, less force. Close together, more force. So in kind of more scientific or mathematic terms, we'd say that the electric force is directly proportional to charge. So directly proportional just means that if charge goes up, the force goes up as well. So the larger charges that you have on your objects, the stronger force that you're going to get. Electric force is also what's called inversely proportional to the distance. Inversely proportional means the opposite of directly. It means that as one number gets bigger, the other number gets smaller. In this case, with distance, with our electric force, the further apart we are, the weaker the force. So if the distance gets bigger, the force gets smaller. And that's what we mean by inversely proportional. It means like opposite proportions. One goes up, one goes down. As opposed to directly proportional, which is where when one goes up, the other one goes up too. So there is a formula in order to calculate this force. You guys don't have to, I don't think we're ever going to use this for like homework or something, but I just wanted to show you exactly how it works. So the force, the electric force, which what F electric means over here, is equal to K, which is just this constant, which means just a number that you plug in, times the multiplication of the two forces. So Q1 is the size of the force on your one charge, and your Q1 is the size of one charge. Q2 is the size of the other charge. You multiply them together to get the total charge, and then you divide it by r squared, where r is your distance. So again, bigger forces means you're going to have a bigger overall number and a bigger force. Bigger distance means that you're going to have a smaller overall number, right? If you have a really big number on the bottom of your fraction, that means that your total number is going to be small. So charges make a force go up when they are big. Distance, when it gets bigger, the force gets smaller. So electric force works really, really well when you have two forces that are really close to each other. You can get a really strong electric force if you can make the distance between your charges very, very small as well. So the closer that they get to touching, the bigger the force becomes. So because objects will exert this force at each other over these small distances, they form what's called an electric field. So an electric field is just the area around a charged object where forces will be exerted on another object. So an electric field is basically just how close objects have to get to each other before they can start repelling or attracting each other. So that's, if you ever see diagrams where they have like objects and they have all the little circle lines going around them, those are meant to represent kind of their electric fields. Again, you don't really have to know how to read this or know exactly what it means. Just know that the electric field is the area around the object where the force starts coming into play. All right. So when we're talking about forces, we're talking about charging up different objects. Some objects become more negative or some objects become more positive. So an example, or a couple different examples of how this works, the different types of charged objects we can have. Our first one, our most basic one, is a neutral atom. So neutral atoms don't have a charge on them because they have an equal number of electrons on protons. So those guys end up canceling each other out. So for example, we have the atom sodium. It's a pretty small atom. It only has 3 protons and 3 electrons. So remember, protons were our positive charges and electrons were our negative charges. So we have 1, 2, 3 positive charges and 1, 2, 3 negative charges. We have an equal number of positive and negative charges. So our total overall charge on our sodium atom is 0, right? We don't have any imbalance between the negatives or the positives. They're completely balanced out. They're completely balanced with each other. For every positive, we also have a negative. So the positives and the negatives cancel each other out in terms of charge. So we have an overall total charge of 0. So neutral atoms have 0 charge because they have this balanced positive and negative. Sodium has 3 and 3 of each, so sodium has 0 overall charge. It is a classic neutral atom. So that's sort of our base level. What about when we do start messing around with our charges? So the way that objects get charged, the way that we can make an object charged, is by changing the number of electrons on that object. So again, the only thing that changes is electrons. So the protons never leave an atom or go to different places. Protons stay put. It is only the electrons that move around. So if we go back to our sodium example, sodium has 3 protons, 3 positive charges. But if something happens and sodium gains a couple extra electrons, like say 2 more, now we have 3 protons and 5 electrons. So if we have lots of electrons, but not as many protons, what is our overall charge on this sodium atom going to be? Are we going to have a positive or negative charge on this atom?
Negative?
Negative, exactly. Because we have more negative charges than positives. So our negatives are kind of overbalancing versus our positives. So our overall charge on this guy will be negative. We have lots of negatives, but not as many positives. What if we look at a different atom down here? This atom has lost a bunch of electrons. So it used to have more electrons, but now it has lost some. So this atom has 7 protons, 7 positives, and 2 electrons, 2 negatives. So this atom down here, oh, Gerson beat me to it already, but yes, he is correct. Gerson is correct. This atom will be a positive atom because we have more positives than negatives. So think about it as kind of tipping the scales in one way or the other. On this one, our scales are tipped toward the positive side, so we're going to have a positive charge. On this one, the top one, our scales are tipped towards the negative side, so we're going to have a negative charge. Again, we can only change the charge of an object by gaining or losing the electrons. So atoms will always have the same number of protons. They will just gain extra electrons and become negative, or lose some of their electrons and become positive. The electrons can move, the protons and the neutrons cannot. All right. Any questions so far on our neutral atoms or how atoms become more positive or more negative?
No, sir.
All right. Cool. So the way that we measure charges, the way that we measure exactly how much charge that an atom or a material has, is through units called coulombs, named for probably the old white guy that came up with the idea of measuring charges. So one single coulomb is the charge that you would get if you took 6.24 times 10 to the 18th electrons all together. Again, electrons are super crazy, itty bitty, microscopic. So if we put millions and billions of electrons together, so this would be 6, 2, 4, and then 16 zeros after that. That's more than like 6 trillion. So if we put a bunch of electrons together, we can end up with 1 coulomb of negative charge. The same thing is true for protons. If we got this many protons together, we'd have 1 coulomb of positive charge. So if you ever see like charges written down and they'll be written as some sort of C, like 6.24 C, that is regarding how many coulombs of charge that you got. And it's just a representation of the total number of electrons or protons that you have in your material. So we've talked about how objects become charged, right? We talked about you have to move the electrons around to either have there be too many electrons or too many protons to give you the negative charge or the positive charge. But how do you make this movement happen? How is it that you can get these electrons to move from one material to another? So there are 3 main ways that objects can become charged. There's friction, conduction, and induction. We'll go through each one of these individually, but again, remember, in each of these, only the electrons are moving. So usually this has to do with 2 materials interacting with each other. One material loses some of the electrons and becomes positive. The other material takes those electrons and becomes negative. So we've talked about what it means to have a charge. Now we're going to talk about how do we make things become charged. So again, when you're creating these electric charges, you're just moving the charges around. You're just moving those electrons around. And again, physics is all about how things move. And so the physics of electricity is looking at how these electrons move. So you're moving these electrons away or towards certain materials. So one object ends up with a whole bunch of electrons and becomes negatively charged. And the other object has lost a whole bunch of electrons. So now it is positively charged. So charging by friction is one way that you can make previously neutral materials become charged. And it's literally just by wiping 2 materials together, which, depending on the material, causes some electrons to be wiped from one object onto another. It's like if you use a cloth, if you're like cleaning off a ruler, then sometimes, depending on what type of cloth and what type of ruler that you've got, electrons move from the cloth to the ruler. So we rub down our ruler, and now, before we had balanced protons and electrons on both materials, but now the ruler has gained a whole bunch of the electrons that it's taken from our washcloth right here. All right, so friction is literally rubbing things against each other and creating a charge that way. The electrons from one object are literally being rubbed onto another object, ending up with one that has more electrons and is negative, and one that now has more protons than electrons, and it becomes positive. So some other common examples of friction are like if you've ever like been under like a blanket, especially in the wintertime, and you've got the heater going in your house, you pull the blanket on you and you can kind of feel the little charges. Or if you like rub your feet against the ground and then touch a doorknob, you get that static electricity or that static shock, right? It also happens to me a lot of times, like coming out of the car, like just the friction between me and the car seat getting in and out. Then I go to close my car door and I touch that metal and it's like, ow, shocked my hand. It's because of the buildup of electrons on my skin that I took from the car seat. And then when I touched the door, all those electrons shot over to the door, which is what makes that little spark. If you've ever, sometimes I see it when, especially in the nighttime at winter, if you have like a really fuzzy blanket, like a wool or like a really thick fuzzy kind of blanket, especially in the winter when your heater's been going and the air gets really dry in your house because you have that heat pumping, dry air helps those charges move due to friction. And so I've seen it before where I can just like pull up that big fuzzy blanket over me. And then when I move my hand underneath, I can see a whole bunch of little charges going off. Like I see like a whole bunch of little sparks happening between my hand and my arm and this big fuzzy blanket. And that's because of the charges that are being rubbed off onto me by the blanket. You can also see this a lot if you're playing with like a balloon and you like rub it against your hair. Your hair then sticks to the balloon because now you have, by rubbing the balloon, you've caused friction, which has moved some electrons between your hair and the balloon. So again, when the electrons move, now we have different charges, and the different charges attract each other. So that's why your hair will like stick to a balloon after you rub it, is due to those opposing charges that become attracted to each other. So that's one way in order to build up charge from one object to another, is by literally just rubbing them together. You can also charge things up by conduction or by touching. So friction was rubbing, so we had two uncharged objects, and then we rub them together, and now they're charged. Conduction happens when you take an uncharged object and touch it to something that is charged. So you have an uncharged piece of metal, like a, I don't know, piece of metal, like a metal scrap. And you have this charged rod, or maybe that charged cloth from earlier that lost all of its electrons and was really positively charged. You can touch the metal to the glass rod or to the washcloth, and the electrons leave from the metal, go over to the glass rod, and now you've just made your metal charged by touching it against something that was already charged. So friction was two uncharged objects that become charged. Conduction is when electrons move through direct contact. So you touch something and it causes the electrons to go from one place to the other. This is basically what happens when you get that static shock from the doorway or from like grabbing onto a metal door handle, is because you are charged, the metal on the door is not. And so when you touch it with your charged up finger, you get that shock of all the electrons leaving from you and going onto the metal. So you cause the metal to become charged when you touch it. So friction is rubbing. Conduction is touching one charged thing to something that's not charged. And then we also have induction. Uh-oh, it messed up my text. That's a little better. So induction is what happens when you have a charged, uncharged object, similar to the conduction earlier, and they move electrons around, but they didn't come in direct contact. So, for example, let's say that you charge up a balloon through friction. So you take the balloon and rub it on your head, and your balloon gets very negatively charged. It's taken all those negative charges from your hair. If you take that charged up balloon and hold it close to little pieces of paper, like confetti paper kind of stuff, without touching it, the electrons will travel from the balloon to the paper. And now the electrons just left the balloon, so the balloon's positive. The electrons are in the paper, so the paper's negative. And so when you bring the balloon in close, you can actually see the paper will then be attracted to the balloon. So you can bring the balloon close and the paper will bond with the balloon. That's because without even touching, electrons moved from the balloon to the paper. The balloon became positive, the paper became negative, and as we've been talking about, opposite charges are attractive. They attract each other. So induction happens without touching, without directly contacting a charged object. So we have friction, which moves electrons around by rubbing things together, literally wiping the electrons from one object to another. We have conduction, which happens when we touch a charged object to something that's not charged, which causes the electrons to move. And we have induction, where electrons move just by holding a charged object close to an uncharged object. One important thing to note is that whenever you're charging something, either with a negative or positive charge, we have what's called a conservation of charge, meaning that no charges are created or destroyed. So the electric charge, so let's say that you rub the balloon on your hair and the balloon becomes negatively charged. The balloon didn't just all of a sudden create a negative charge on itself. It became negatively charged because it took the electrons from your hair. So the overall total number of electrons and protons between the two objects stays the same. It just so happens that the electrons move from one atom to another, right? If we have two different atoms that each have, I don't know, let's say 10 protons and 10 electrons. And we have 7 electrons move from one atom to another. So now we have an atom that has 17 electrons and an atom that has 3 electrons. We start off with a total of 20 electrons across the two, and we ended up with a total of 20 electrons, right? We started off with 10 and 10, but now we have 17 and 3. We have the same overall number of charges, they're just rearranged differently. So that's what we mean when we say that no charges are created or destroyed. It means that we can't just get rid of some electrons, or we can't just make electrons out of nowhere, right? The electrons have to come from somewhere. They come from those other atoms. Like in this case, we have a sodium and a chloride atom. The chloride atom takes an electron from the sodium. So we end up with the same total number of electrons, right? I think if I remember correctly, chloride starts with 17 and sodium starts with 11. So that's 28. One electron hops over. So now chlorine has 18 and sodium has 10. That's still 28. We still have overall the same number of electrons. It's just that we moved around how they're distributed. So now chlorine has a negative charge because it got that extra electron. And sodium has a positive charge because it lost that electron. So we just moved one electron around in order to create positive and negative charges. But we didn't get rid of it. We didn't create a new electron out of nothing. We have the same overall number. We just moved how they're distributed. So we can't make or destroy charges in electrons and protons. We just move around our electrons to create negative charges on things that have extra electrons and positive charges on things that have too few electrons. All right, so there are some things that can affect how these charges get moved around. So we have conductors, which help charges, and insulators, which slow down charges. So a conductor, an electrical conductor, is a material where charges can easily move from one end to the other. So conductors are things that electricity can move fairly easily across the surface of the conductor. So metals are very, very common good conductors. The way that metals are set up, their electrons can very easily move all around the surface of the metal. Which is why if you ever look at the wiring in your home or the wiring in your cords that charge up your phone or turn on your lights or stuff like that, it's pretty much all metal wiring in there. Probably some combination of copper and aluminum, which are extra super good conductors. So like if you open up this lamp wire, you have the metal prongs that you plug into the wall, and then you have the little wire cables that travel through inside of this kind of plastic rubber sheath. And those are what are actually carrying the charge. So in conductors, charges move really easily. They can go from one end to the other very quickly without really being stopped or slowed down. Insulators are the opposite. In an insulator, charges cannot move easily. They are stopped or super slowed down from moving. So unlike conductors, where the electrons can just move freely, nothing stopping them, in insulators, the electrons are stuck. Usually the atoms of the insulator don't really want to move their electrons around. And so it's hard to get any charge to flow through them. That's why even though it's the little metal cables that are carrying the charge through the wiring, that go into your lamp or your phone cord or whatever it might be, there's almost always some sort of insulating material around them. So like the white part of this lamp cord, or the red or green part of these cables down here, these are either plastic or rubber insulators. What they do is they stop you from hurting yourself if you touch it, because charge can flow fairly easily through the human body. We are okay conductors. We don't want that to happen. We don't want lots of extra charges going through your body. That's how you get shocked and electrocuted, and that's not good. So we have these insulators, usually made out of some combination of plastic or rubber, that help to stop the charge from moving. So charges can't really pass between the metal wire and the plastic or rubber insulator into your hand, into your body. That's what the insulators are there for. So plastic and rubber are a really good one. Glass, wood is a very good insulator. So conduction and insulation also a lot of times applies to heat as well as electricity. So this is why if you leave your wooden spoon in your boiling pot of water for a couple minutes, it's usually fine to pick it up and keep stirring. Versus if you did that for a metal spoon, you'd burn your hand. Same thing with if you poke things into the wall outlet, which obviously is a bad thing to do. Don't do that. But if you ever did do it with like a fork or something like that, if you use a metal fork, you're going to get shocked because the electricity is going to very easily pass through the metal conductor that is the fork into your body. Whereas if you do it with a plastic fork, you can shove that into the wall outlet all you want. You might damage the outlet, which wouldn't be good, but you probably aren't going to get an electric shock because plastic is an insulator. Electricity does not flow through plastic very well. So conductors move electric charges and electrons very easily and quickly. Insulators do not. They like to hold on to their electrons and not let them move around. So the different types of charges and electricity that we've talked about today are what's known as static electricity. So you usually think of static electricity as the type that I was talking about today, when like you touch wood, or not wood, you touch like metal on your car or something, or the doorknob, after you get a little bit of charge and you get that static shock. But more generally, kind of more broadly, static electricity just refers to when there's a certain buildup of charge on an object, but that charge isn't moving. So static is a science word that essentially just means not moving, staying still.
Never knew that.
Like the charges that we've been talking about today. You rub your balloon on your hair, and the balloon gets charged and your hair gets charged, but that charge isn't moving, right? The charge doesn't move from the balloon out into the air, or it doesn't move like through your hair down through your body. It just kind of sits on where it got built up. It sits on the surface of the balloon and it sits in your hair. It doesn't move somewhere else. So that's the kind of charges that we've been talking about so far today, is when a charge gets built up on a certain object or in a certain area, but it's not like a moving current. It's not moving electricity. That is what we're going to be talking about on Thursday. That is called electric current, and that's when you have electricity moving through a circuit, moving through a certain area. What we've been talking about so far today is static electricity. Charges get built up and then sit in a certain area. So the actual shock that you get when you build up charge and then touch something that shocks you is not called a static shock in science. It's called electric discharge. So Sometimes it happens kind of slowly. Like if you ever put clothes through a dryer and they were all moving around together in that hot, dry air. Sometimes when you're taking them out, you can kind of feel a little bit of that electric charge on there, right? It feels a little bit tingly, especially if you're doing like a bunch of big like sweatpants or blankets or something like that. Sometimes it happens quickly, like if you're Mr. Stanley and you're driving your car for a little while and then you get out and go to close the door and ooh, got you on the finger. Or if you wear big fuzzy socks and shuffle your way across the carpet and then touch a doorknob, you get that little static shock of electric discharge. Sometimes, like if you're paying attention to the weather last night, it can happen quickly in a very big way up in the atmosphere. And we call that lightning. So lightning happens because of buildups of charge in the atmosphere that are then let go of in a very, very short amount of time. It's the same idea as shocking yourself on a doorknob or a car door, just on a way bigger scale. So super basically, the way that lightning works is you have all these storm clouds that come rolling in across the sky, right? And storm clouds are made up of lots of tiny different water droplets and ice crystals and stuff. And all of that air and ice water is all moving around together. So we have some friction going on between all these different tiny particles. And as we just talked about, we can use friction to build up charge. It just so happens that in clouds, we tend to build up, when we have that friction between all these little parts, the bottom of the cloud tends to develop a negative charge, and the top of a cloud tends to develop a positive charge. So we have all these little electrons from our water and our ice and our air that are moving and congregating in our cloud down here at the bottom. So through induction, remember when we build up a charge without touching anything, that can happen even across big distances, like from the ground to the sky, when we have this much charge being built up in the air. So we have the negative charges hanging around here at the bottom of the clouds. That can induce some positive charge on the ground down here. And when that difference gets big enough, you have that rapid discharge with the bright light and the bolt that comes down, known as lightning. So sometimes that lightning bolt comes and hits the ground. Most of the time, like if you saw last night, there's a lot of lightning happening between the different parts of the clouds. Because again, you still have negative down here on one cloud. And if that negative gets close to the top part of the positive of the other cloud, you can have that discharge happen there as well. So the lightning that you see during a thunderstorm, like the one we had last night, it's all due to the movement of these electric charges. The clouds build up different areas of different electric charge. And then when they come close to the ground, or they come close to the opposite area of another charge, they have this electric discharge, and this big bolt of lightning shoots from one area to another. So just some other kind of fun facts about lightning. It tends to hit high points on the Earth's surface because it wants to take like the shortest route to get to the ground. And going all the way from the cloud down to the soil is a long way. So if there are things like structures or buildings or trees that provide a little bit easier path, that's why lightning tends to hit those things. So in some cases, in areas that see a lot of lightning that we're trying to not have damage the area, they make lightning rods, where we have a big rod, like even on the top of this building here, we have a lightning rod that connects to the ground that allows lightning a safe pathway from the sky down to the ground. Damage happens with lightning whenever it passes through like your house, because that electricity goes through all your circuits and is way too big of a charge for your circuits to handle. So that's why like electronics and stuff can get messed up if it gets hit directly by lightning. Instead, if we reroute that lightning through a nice little cable directly into the ground, it bypasses all of that nice machinery that we were trying to make sure that it doesn't hit. So it's totally fine for the earth to absorb all that lightning damage so that our structures and buildings and electronics don't have to. So that's how, even though tall buildings are more likely to get struck by lightning, we can prevent them from getting damaged by the lightning by giving those electric charges an easy way to reach the ground that doesn't involve going through a building. Alrighty, and I think that will take us to our end of our notes for today. So does anybody have any questions at this point about electric charges, how they get made, positives and negatives repelling and attracting each other, anything about electric charges that we've talked about so far today that you have questions about?
No, Mr. Stanley.
All righty. So the couple things on the homework that I wanted to bring up. The homework for today is hopefully fairly straightforward. You can go back to these notes or this video if you want to. The first part just talks about the different parts of the atom and what parts of the atom are positively versus negatively charged. There's a question about a neutral atom versus an atom that has an electrical charge on it. There's a part where you have a negative atom, a positive atom, and a neutral atom. And I want you to tell me, how does the number of electrons compare to the number of protons? Does this type of atom have more electrons? Does it have less electrons? Or does it have the same amount of electrons as protons? And then finally, there's a question about how charges move, or what types of charges move from one area to another. And then finally, there's some questions about charge interactions and insulators versus conductors. So that is the homework for tonight. Again, should be pretty easy and straightforward, especially if you go back to the notes or if you need to go back and watch this video. That is fine. One thing, important thing that I wanted to mention regards the homework for tomorrow. So if you guys remember it might be hard to remember because about a year ago around spring break is when we all left for the break and then never came back in person. But you might remember before the break, we were doing a whole bunch of different writing assignments for the Excel Center. And so this is something that the Excel Center does every springtime, is collects writing assignments from students just to kind of see how people have been progressing and their ability to write so far while they've been at school. So one thing about this is that we want to make sure that nobody's getting any sort of extra help from Microsoft Word or Google or anything like that. And so you have to turn in your writing assignment homeworks on a handwritten sheet of paper. So for example, for tomorrow's assignment, I want you to handwrite on a piece of paper and just kind of put in your own words some parts of the notes that we talked about today. Specifically, how an object becomes charged. So what happens that causes an object to become positively or negatively charged? And what happens when you have different types of charges that interact with each other? So either the same charge or different charges, what happens when they get close to each other? Again, this is a writing assignment that we're collecting at the Excel Center as part of kind of doing this every spring to see people's progress. And so please, 3 things that I wanted to mention. 1, again, handwritten, so in your own words, written out on just a piece of notebook paper or printer paper. A couple other things that I wanted to mention. Please make sure you have your name, so your full first and last name, usually somewhere at the top, and also the date. So whatever date that you write your paper, make sure you write that down on your paper as well. If you could get it to be about a page long, that would be perfect. I know sometimes you kind of run out of steam or run out of ideas at that point, but feel free to use any way that you want to describe or provide details or examples of these charges and how things become charged. If you can't quite get to one full page, that's okay. But the more that you're able to write, the better that we'll be able to kind of take a look at your work. Again, handwritten, pencil, pen, whatever works for you. Make sure that you're doing this in your own words. So we don't want people just copying down definitions from the notes or copying down the answers from their Google Slides. So however you would describe how things become charged and what happens when they interact. You can go back if you want to look at the notes for reference and kind of refresh your mind on how to do this. But please do your best to put it all in your own words. When you're done with your assignment and you want to turn it in, you can take a picture of it on your phone, and then you can either email that picture to me, you can text it to me, or you can upload it right here on the Google Classroom as part of the assignment. Dang it, I was just about to say something. Oh, so this does have a grade associated with it, but it is not a grade of how well you described charges. It's literally basically a completion grade. As long as you turn in the assignment to me, then you'll get full credit for getting it turned in. I'm not necessarily looking to try and make sure, do you have a perfect understanding of how this stuff works? I just want you to do your best at writing it down in your own words and then turning it in to me. So again, that'll be the assignment for tomorrow for your daily attendance credit, is handwriting on a piece of paper how objects become charged and what happens when you bring positive, positive, negative, negative, or positive and negative charges together. All right, so does anybody have any questions about either the assignment for today or the handwriting assignment for Wednesday?
No, mister, I'm good.
All right, great. Thanks, Gerson. This probably will not be the last one of these that you see in this class. I'm planning on having there be 1 or 2 more by the end of the term. So just keep your eye out for them and know that you'll have a couple more coming by the end of next week as well. Alrighty.